Have you ever looked at a map and just wondered, why are some places warm and others cold, even when they're on the same line? Well, it turns out it's all thanks to this incredibly powerful, kind of invisible engine that connects our wind, our oceans, and our climate. So today, let's pop the hood and see how it all works.
Okay, so let's kick things off with a bit of a mystery. I want you to picture London, England, and then picture Nain in Labrador, Canada. Now, they're sitting at pretty much the same latitude, so you'd think their climates would be similar, right? Nope, not even close. London gets these mild, rainy winters, while Labrador, well, its winters are just brutally cold. So what gives? How is that even possible?
Well, the secret isn't in the sky, it's in the ocean. See, hidden just beneath the waves, there's this massive, colossal current. Think of it like a literal river of heat flowing right through the Atlantic. It's basically a giant heating system for an entire continent, and we are about to follow its incredible journey. All right, so first question. How in the world do you get an entire ocean to start moving? Well, it all kicks off with something you might not expect. It's the wind. The atmosphere is really the primary engine that gets the ocean's surface going. Just picture it. You've got these steady winds blowing across the surface of the ocean. They're not just gliding over the top. No, they're actually grabbing the water, dragging it along with them because of friction. It's this huge transfer of energy. But, a simple push like that, that's not enough to explain the incredibly complex patterns we see all over the globe. Okay, now this is where things get really, really interesting. That simple push from the wind gets a massive planetary scale twist. This twist is what organizes all that moving water into these enormous spinning systems. So let's break down the two key ingredients that make these giant gyres happen. Ingredient number one, you need a consistent, reliable engine. And for that, we have the trade winds. These are super steady winds that blow from the east on both sides of the equator. Think of them as this relentless, powerful force that gives the ocean water its first big shove, pushing it to the west. All right, on to ingredient number two, the Earth's own spin. It's a funny thing, but because our planet is constantly rotating, any object that's moving across its surface gets deflected. It doesn't matter if it's a rocket or a huge mass of ocean water, it gets pushed sideways. This is what we call the Coriolis force. And the key thing to remember is, in the northern hemisphere, that push is always to the right. So let's put it together. What happens when you combine that steady westward push from the trade winds with that constant rightward turn from the Coriolis force? Well, you get a gyre. These are just enormous systems of circular ocean currents, basically massive spirals of water that dominate every major ocean on the planet. Okay, to make this real, let's actually trace the journey of one of the most important gyres on Earth, the North Atlantic Gyre. So it all starts as the North Equatorial Current, getting pushed west by those trade winds. When it slams into the Americas, that Coriolis force kicks in, turns it right, so northward, and it becomes the super famous Gulf Stream. From there, it travels all the way across the Atlantic as the North Atlantic Drift, carrying all of that incredible warmth toward Europe. And finally, it turns south, becoming the cool Canary Current, which brings it all back to the start and completes the loop. Okay, so now that we get how these massive gyres work, we can finally go back and solve our little London versus Labrador puzzle. Because this isn't just about water sloshing around. This is the planet's entire climate control system in action. And here's the answer. Remember that North Atlantic Drift we were just following? That's it. That's the final leg of that river of heat we talked about. As it flows past Europe, it just releases a massive amount of warmth into the atmosphere. And that is what gives Great Britain and northwestern Europe those mild climates. Take that away, and yeah, their winters would look a whole lot more like Canada's. But it's not just about warming things up. It works both ways. Cold currents have the exact opposite effect. As they bring that chilly water down from the poles, they cool the air above them. And this creates some really, really unique climates along the coastlines they brush up against. Now, this part is just fascinating. When I say desert, what do you picture? Probably hot, sandy, dry, right? Well, the deserts that get formed by these cold currents, like the Atacama Desert in Peru, they are completely different. The cold ocean water chills the air right above it so much that the air becomes super stable and it just can't rise up to form rain clouds. So what do you get instead? You get really high humidity and tons of fog. I mean, these are cold, damp, foggy deserts. How wild is that? So everything we've looked at so far has been about water moving horizontally, right? Across the ocean's surface. But the wind and the Earth's spin also team up to create some really powerful vertical movements. And that brings us to the phenomenon of upwelling. So what is upwelling? Well, to put it simply, it's a process where deep, cold, and really nutrient-rich water gets pulled all the way up to the surface. It's an absolutely critical process for marine ecosystems. And guess what? Once again, it's all driven by the wind. So how does this actually happen? Okay, picture a wind blowing parallel to a coastline. We're in the northern hemisphere, so the Coriolis force is going to push that surface water to the right, which means it's pushing it away from the shore. Well, something has to fill that gap, right? And what fills it is that cold water from down below rising up to take its place. Simple as that. And trust me, this has a very, very real effect that you can actually feel. There's a great line in our source material that says if you're a swimmer who's used to the waters along the mid-Atlantic states, well, you might find a dip in the Pacific off Central California's coast to be a chilling surprise. And here's the why behind that chilling surprise. In August, when a beach on the Atlantic coast might be a pretty pleasant 21 degrees Celsius or about 70 Fahrenheit, the water off Central California, thanks to all that upwelling, it's a frigid 15 degrees Celsius. That's only 60 degrees Fahrenheit. That is the incredible power of the wind, literally pulling deep ocean water right up to the surface. So when you put it all together, from these huge spinning gyres to the surprising chill of coastal upwelling, you start to see a planet that is just in constant dynamic motion. The atmosphere and the oceans, they're locked together in this incredibly intricate dance. And the scale of this dance, I mean, it is just staggering. Get this. Ocean currents are responsible for moving a full 1/4, 25%, of all the heat that gets transported from the warm tropics up toward the poles. I mean, that is a fundamental piece of the puzzle that makes our planet habitable. Really, what this all comes down to is a beautifully complex system. You have the wind pushing the water, the planet's spin giving it a turn, and the result of all that is this massive movement of heat and cold that regulates the climate for the entire globe. It's an incredibly delicate balance, one that's been fine-tuned over millions of years. And that, of course, leaves us with one final and really crucial question. We've seen how this incredible engine works when everything is stable, but we've also said it's a delicate balance. So what happens if that balance gets disturbed? What happens to Europe's mild weather, or to those foggy deserts in Peru, if the engine starts to run differently? That's the big question we're left with.